acting on B towards A is acting on B downwards, while B is acting on A in the opposite direction. But then the two of them are equal. That's what Newton's law of motion, Paul's law of motion is trying to say. So now I can say when we have FAB, which means the force that A is acting on B will be equals to the negative force of B acting on A. This is simply what Newton's law of motion is explaining to us. That's for every action, there is an equal but opposite reaction. So the reaction is equal, but then they are opposite in direction. So which means, and since it's opposite to the negative value of the action, the reaction will be the negative value of the action. So let's say A is acting 5 Newton on B. It means B will also be acting 5 Newton on A, but in the opposite direction. So which means A will be equals to minus 5 Newton. So which means the force BA, which means the force that B is using to act on A, will be in the opposite direction as the force A is acting on B. So which will be minus 5. Actually, the magnitude is 5 Newton, but then the direction, which is just trying to tell us that it's in the opposite direction. That's why we're having this negative value. Okay, so that's Newton's law of motion. So now we'll be taking, before we move to working examples, within law of conservation of linear momentum. We did linear momentum and impulse in the last class. So we'll be doing law of conservation of linear momentum. So what does the law of conservation of linear momentum says? Okay, the law of conservation of linear momentum says that during collision, when colliding objects are not acted upon by an external force, the sum of their momentum before collision is equal to the sum of their momentum after collision. Okay, what does this mean? It simply means when two bodies are moving and they collide, like say two balls are moving and they collide together, if they are not acted upon by another external force, then their collision, that's their momentum before collision, and their momentum after collision will be the same. Now, let's say we have a ball one. Let's say we have ball one with a mass of m1, and it's moving with a velocity of u1. And then we have ball two with a mass of m2, and it's moving with a velocity of m2. So let me say this is my ball one, and then this is my ball two. So now they are moving. Let me say ball two is coming from this direction, and then ball one is coming towards this direction, and then they collide together. Now, if no external force is acting on these two balls, let me say friction or something, it means their momentum before collision will be equal to their momentum after collision. Are you with me? So now, what's momentum? Momentum is the product of the mass of a body and its velocity. So now, which means the momentum before collision. Let's say after colliding, m1 velocity became v1. Why after colliding, the velocity of ball two became v2. Now, their momentum, what's the law of conservation of linear momentum is saying, their momentum before collision will be equal to their momentum after collision. That's the sum of their momentum. So now, what's the sum of this momentum? Since momentum is product of the mass and velocity, that's m1 times u1, then plus the momentum of ball two before collision, m1 times m2 times u2, will be equal to the sum of their momentum after collision. Now, this is the sum of the momentum before collision. That's the momentum of ball one plus the momentum of ball two before collision. Now, I want to add it up with the momentum after collision. Now, this will be m1 v1, which is the momentum of ball one after collision, because this was the velocity after collision. After it has collided with ball two, its velocity changed from v1 to v1. So now this is the momentum after collision of ball one plus the momentum after collision of ball two. So now this is the representation of law of conservation of linear momentum. M1 U1 plus M2 U2 plus M3 U3, as much bodies as you have, maybe 3 bodies, 4 bodies, you keep adding them. That's the number of bodies you have. The sum of their momentum before collision will be equal to the sum of their momentum after collision, provided there is no external force acting on it. So that's law of conservation of linear momentum. So now let's move to working examples. Working example. So we have example 1. A body of mass 100 gram moves with a velocity. A body of mass 100 gram moves with a velocity of 10 meters per second and collides with a wall. If after collision, it moves with a velocity of 2.0 meters per second in the opposite direction, calculate the change in momentum. Okay, so the first thing I'll do is I'm going to take down the parameters. I'm going to take out the parameters. So the body of mass 100 gram. So the mass of the body is 100 gram. So, and then it collides with a wall with a speed of 20 meter per second, with a speed of 10 meter per second, sorry, with a speed of 10 meter per second. After colliding with the wall, it moves with a velocity of 2 meter per second. It's 2 meter per second. That's after collision. Then, in the opposite direction, calculate the change in momentum. Firstly, you have to understand the question. A body of mass 100 gram moving with a velocity of 10 meter per second. This is it. If collides with a wall, if after collision it moves with a velocity of 2.0 meter per second in the opposite direction, calculate the change in momentum. Okay, now so and change in momentum. We said change in momentum is mv minus mu, right? So now this is the velocity at the beginning. Why this is the velocity, or you can say this is initial velocity and this is final velocity before colliding after collision. So now the SI unit of my 100 gram, which is standard international unit of mass, is not gram but kilogram. So what I'm going to do here is I'm going to convert this 100 grams to kilograms. So how am I going to do it? I'm going to divide it by 1,000. So I'm going to divide 100 divided by 1,000, which is going to give me 0.1 kilogram. So which means my mass is 0.1 kilogram. I converted this gram to kilogram by dividing by 1,000. So I have 0.1 kilogram. So what I'm going to do is, firstly, since m here is common, I can say m open bracket v minus u is my change in momentum. So I can write it like this, change in momentum. Don't forget, momentum is represented with p. Momentum is represented with p. Okay, all right. So now my m is common here. So my m is 0.1. Now my v here is 2. Now don't forget, it said it bounces or it moves with a velocity of 2 meter per second in the opposite direction, which means one of my velocities is going to be a negative sign. So this will be minus 10. So this will become 0.12 plus 10. That's minus times minus. Why this becomes 0.1 times 12? And this is going to give me 1.2 Newton second or kilogram meter per second. This is it. So now, how did I come up with this? Firstly, the question says find change in momentum, and change in momentum is final momentum minus initial momentum. So now what's my final momentum? Firstly, my mass is the mass of the body is common. So I bring this out, and the mass of the body is 0.1. Now I said because after collision, the body moved in the opposite direction. Don't forget when I said opposite direction, I said it's going to be negative. So because it's moving in the opposite direction, either the initial velocity is going to be negative or the final velocity is going to be negative. Now here, I used my initial velocity to be negative. Now I can also do it the other way around and allow my final velocity to be negative. So which is going to be 0.1 times minus 2 minus 10. So this will be 0.1 times minus 12. And this will be minus 1.2 Newton second. So since momentum can't have a negative value, my answer will be 1.2 Newton second or kilogram meter per second. So you still have the same answer. So what you just have at the back of your mind is after collision, since it's moving in the opposite direction, one of the velocity is going to be a negative sign. So that's what I did here. I made my initial velocity to be the negative sign. That's minus 10. So minus times minus became plus, and this becomes 2 plus 10. And this is 12. So 0.1 times 12 is 1.2 Newton second. So the answer to the question here is option B, 1.2 Newton second. So it depends on the unit you are given in the question. You can be given Newton second, and you can be given kilogram meter per second. So the two, they are still the same thing. Okay, so let's move to example 2. I'm going to clean this. 0.05 kg. A lead bullet, or you say lead, a lead bullet of mass 0.005 kg is fired with a velocity of 200 meter per second. So the first thing I want to do is I want to write down my parameters. So right now my parameters, I say the mass is 0.05 kg. Why the velocity is 200 meter per second? Velocity is 200 meter per second. So I have it here. A lead bullet of mass 0.05 kg is fired with a velocity of 200 meter per second into a lead block of mass 0.95 kg. So now I'll take the mass of my bullet as M1 and I'll take the mass 5 kg. Okay, right? So now this is it. Given that the lead block can move freely, calculate the final kinetic energy after impact. So now, at first, the lead block is at rest. So now, after collision, the lead block can move freely. Now they ask me to find the final kinetic energy after impact. So what I want to do is I'll name this U1 and then my U2, since the lead block, as at when it was colliding or before the collision was at rest, it means the velocity of the lead block will be 0 meter per second because it was at rest before collision. Are you with me? So because the lead block was at rest before collision, the initial velocity of the lead block is going to be 0 meter per second. Now what I want to find is the final velocity. So since the lead block can move freely, it means the bullet is going to move and it's going to move at the same velocity as that of the lead block. Are you with me? So now they are going to have a common velocity. So now I'm going to say, using the law of conservation of linear momentum that I said like a few minutes ago, M2 U2 is equals to M1 V1 plus M2 U2. So this is what we have, the law of conservation of linear momentum. So what I'm going to do here is I'm just going to replace all of my values here. I have my M1, I have M2, I have U1, and I have U2. And I'm looking for V. So here, since the velocity after collision is common, I'll just make this one V. So what do I mean? This will become plus M2U2 is equals to M1V plus M2V this way. So now I'm just going to input the values of my parameters into this place. So M1 is 0.05 and my U1 is 200. So this will be plus. My M2 is 0.95. Why my U2 is 0? Because it was at rest. So now moving here, V is common, right? Okay, so I'll just continue from here. So U is common. Since V is common. So I'll just say V open brackets, M1 plus M2. What's my M1? M1 is 0.05 plus M2, which is 0.95. So yeah, I'm going to evaluate all of this. So evaluating this, don't forget this is a continuation of this. So evaluating this, 0.05 times 200, I think it's going to give me 10. Yeah, 10 plus this times 0 is 0. And this will give me V times, when I add this together, I should have 1. 0.05 times 10 plus 0.95. I have 1, right? So 10 plus 0 remain 10, and then V times 1 becomes V. So my V is equals to 10 meter per second. So now, after collision, the lead block and the bullet and the lead block and the lead bullet both move at a velocity of 10 meter per second. But that's not what the question asked me to find. The question asked me to find the final kinetic energy after impact. So now, if you can remember very well, kinetic energy, what is the formula for kinetic energy? Kinetic energy is half mv squared, which is 1/2 times mass times the square of the velocity. So that's formula for kinetic energy. So what I'm going to do here is, I have my mass. Now, you see, you have to find the kinetic energy. So the kinetic energy of the lead block and that of the lead bullet. So now, the lead block has a different mass and the lead bullet also has a different mass, but then they both have the same velocity. So I can say M1, sorry, 1/2 M1 V1 squared plus 1/2 M1 V2 squared. So now, since this V, the value of my V is common, I can just leave this as this V squared plus half M2 V squared. Sorry, this. So this is 1/2 the mass of the lead bullet times the velocity square plus 1/2 times mass of the lead block times velocity square. So here now, my velocity is common and the half is common. So I can just write it as 1/2 open brackets M1 plus M2. So from here, I'm just going to impute the values. I calculated my V as 10. So this will become 1/2 times 10 times open brackets 0.05 plus, okay, sorry, this should be square. So this will be 10 square times 0. So remember, this is V square. So V square is common. So this will be 10 square. So here I'll have 1/2. 10 square is 10 times 10, which is 100. Then times 0.05 plus 0.95. This is 1, right? So this is 1. So what I'm going to do here is, from here, I have 1/2 times 100 times 1. So which means 1/2 times 100, which will give me 50 joules. Why is it 50 joules? Because I'm calculating energy, and kinetic energy is measured in joules. So my answer is 50 joules, and the answer to the question there is option C. Option C is my answer. So firstly, I calculated the velocity by using law of conservation of linear momentum to get the velocity, the common velocity between the two objects, which is my lead block and my lead bullet. So the common velocity after collision was what I used to calculate my kinetic energy using the formula half mv squared. So after doing that, I got my kinetic energy as 50 joules. So now let's move to another example. Example 3. Example 3 says a 0.5 kg ball the 0.5 kg ball is moving at a speed of 10 meters per second. A 0.5 kg ball is moving at a speed of 0.5 meters per second. A bat hits the ball and the ball rebounds in the opposite direction with a speed of 20 meters per second. Okay, let's take it one after the other. Four. Okay, now, so the question says a 0.5 kg ball. Firstly, I'll write the mass of the ball as 0.5 kg. The 0.5 kg ball is moving at a speed of 10 meters per second. That is the initial velocity or initial speed. It's moving at a speed of 10 meters per second. So here is it. Now, a bat hits the ball. So a bat hits the ball, and the ball rebounds in the opposite direction with a speed of 20 meters per second. So which is 20 meters per second after the rebound or after the collision. If the bat was in contact with the ball for 0.02 seconds, what is the impulse of the bat? Now, if you remember in the last class, I said impulse is equal to force times time. So force times time. And then if you remember also from Newton's law of motion, if you missed the last class, you can just go back to our YouTube channel and then follow up. So I said force, according to Newton's law of motion, is change in momentum over time. So which means I can just replace this force with change in momentum over time. So my impulse will become change in momentum over time times time. So which means this can cancel out this, time can cancel out time, and I have impulse is equals to change in momentum. You can say something like this. Impulse is equals to change in momentum. That's change in momentum, which is the mass open brackets, initial velocity minus final velocity. So I have this as my impulse, and I am to calculate impulse. Okay, so I'm just going to continue from here because I don't want to do this. So I say my impulse is equals to mass change in momentum. So now what I'm going to do is impulse is equals to what is my mass? My mass is 0.5 kg. And don't forget, after the rebound, the ball moved in the opposite direction. So which means one of these two velocities is going to be a negative value. So I'll take this. This will become 20 minus 10. So this will become 0.5 open brackets 20 plus 10. All this is going to become 0.5 times 30. And then 0.5 times 30, when I multiply, it's going to give me 15 Newton second. So this is the unit for impulse, Newton second or kilogram meter per second. So mostly Newton second is accepted for impulse. So now what I did was I used the formula impulse is equals to change in momentum, and then my M is mass, which is 0.5 kg, the mass of the ball, and then times 20 minus 10 minus 10. Why I used minus is because the value, the ball after collision or after rebound, it went in the opposite direction. So which means one of the velocities is going to be the negative, is going to be a negative value. That's why I have negative value here, minus 10 instead of 10. So now when minus times minus give me plus, I have 20 plus 10, 30. 30 times 0.5 give me 15 Newton seconds. So I have my answer as 15 Newton seconds, option C. So now always take cognizance of all of this. When you have opposite direction, always make sure you have a negative sign in the value of your velocities. Because even if you use minus 10 and then use 10, I guess you have the answer there. So you might think you got the answer, but then you're doing something wrong. So when you're working with calculations like this, it's very easy for you to fail it because when you solve it the wrong way or you miss a step, you might still find the answer there in the option. And when you select it, you think you got the right answer. So you have to be careful, yeah, working with all these calculations so that you get the right answers. Okay, so the last example, and then we'll move to another topic. So it's going to be an example 4. So I'm just covering Newton's law of motion with impulse and momentum together. So this will be my last working example, and then we'll move to the next topic. So now this says a ball of mass 800 grams. So the mass is 800 grams. A ball of mass 800 grams moving horizontally with a speed of 5 meters per second. Speed of 5 meters per second, which is 5 meters per second. Okay, all right. Hits a vertical wall and rebounds with the same speed. The impulse experienced by the ball this is very similar to the one we did the first time. Okay, so it hits a vertical wall and rebounds with the same speed. The impulse experiences is rebounding with the same speed. It means my V is also going to be 5 meter per second. So it is rebounding with the same speed. The mass is 800 grams. The velocity it was moving with was 5 meters per second. Then after rebound, it's rebound with the same speed, which means my V is also going to be 5 meters per second. Now, calculate the impulse experienced by the ball. So now, impulse, I said, is equals to change in momentum, which is this M open brackets V minus U. Now, don't forget, 800 grams. My grams is not measured in the standard unit. So I'm going to convert 800 grams to kilograms. So converting 800 grams to kilograms, I'll just divide 800 by 1000. By saying 800 divided by 1000, I have 0.8. So here, my impulse is going to be 0.8, 5 minus 5. That's because it's rebounded in the opposite direction. So this is going to become 0.8, 5 plus 5. And this is going to become 0.8 times 10, which is going to be 8 kilogram meter per second. Like I said in the last example, I said you can use Newton second or kilogram meter per second. So using kilogram meter per second, I got 8 kilogram meter per second, and then my option there is option D. So which means the answer to this question is 8 kilogram meter per second, which is option D. So that's just it. So you just, when you have questions like this, you first fill in the parameters, you understand the questions. So after getting your parameters down, you find which of the formulas are you going to use. So either use, if you have to find change in momentum, or you find the final velocity of the two bodies after collision, then use law of conservation of momentum, of linear momentum. If you have to find the impulse, you use this formula and all of that. So if you miss the last class, you can just do well by going to TPAT's channel on YouTube and rewatching the video, or maybe probably you might have forgotten some stuff you did in the last class. And just go to refresh your memories. Okay, so we're moving to the next topic. Okay, so we're moving to another topic, which is equilibrium of forces. We're moving to equilibrium of forces. When we are talking about equilibrium of forces, say two forces are said to be in equilibrium when their resultant are zero. So now, what do I mean by resultant? Let me say probably the force is acting this way. Let me say a block is here. Let me say this is a block of lead or something. Then a force is moving it this way, another force is moving it this way. Now, let me assume the force moving it this way is A, and the force moving it this side is B. So now, I have force A and force B acting on this block. Let me say this, my block is X, block X. So if force is acting towards the A direction, and then another force B is acting in the opposite direction. Now, these two forces are said to be in equilibrium only if the resultant force of these two are equal to zero. So how is it going to be equal to zero? Since this is moving in opposite direction, this will be the negative value of this. So which means A is equals to minus B. So if A is equals to minus B, it means these two forces are in equilibrium. What do I mean? Now, if I bring it to this other side to become plus, and this will become A plus B is equal to 0. That's it. So when I said forces in equilibrium, it simply means now, for example, this is 5 Newton, and this is 5 Newton. So now A and B are acting in opposite direction. So now A is trying to move this way, and then B is also trying to move this way, which means their resultant would be A minus B. And then what is A? My A is 5, and then B is also 5. So 5 minus 5 is 0. So the resultant velocity, the resultant vector, or the resultant force of forces in equilibrium is always 0. So which means for a force or for forces, it might be more than two forces. It might be more than two forces. It might be 3, 4 forces. So for forces to be in equilibrium, it means the resultant of those equilibrium must be of those forces must be equal to 0. So for forces to be in equilibrium, the resultant of that force must be equal to 0, or the sum of the resultant force must be equal to 0. So now let's move to equilibrium of forces of concurrent forces. Equilibrium of concurrent forces. So when we talk about concurrent forces, what do we mean? Concurrent forces are simply forces that originate from a common point. Concurrent forces are forces that originate from a common point. For example, I have this, I have this, I have this, and I have this. Let me say this is A, B, C, and this is D. So now this is force A, force B, force C, and force D. So now this is an example of concurrent forces. Why? Because they both originate from the same origin O. They're both coming from this point O. So these are concurrent forces. So these four forces here, A, B, C, D, they are concurrent forces. So this is an example of a concurrent force or of concurrent forces. Forces that originate from the same point or that generate or that pass through the same point. So this is example of concurrent forces. So as A, B, C, D, they are passing through the same point or they generate from the same point. That's concurrent forces. So two or more concurrent forces are said to be in equilibrium when the resultant of the forces is zero. So now, let me say this is force A and this is force B. So now these two forces can only be said to be in equilibrium if the resultant of these two vectors is equal to zero. Now I can say this should be C. Now, so I have A, B, C forces. Or I can say F1, F2, and F3. So I have three forces here, A, B, C. So now, for me to get their equilibrium forces, I can rewrite this, or I can reshape this as my A, which is moving in this direction, and this as my B, which is moving in this direction, and then this is my C. So here is C, here is B, and this is A. So now, if you look very well, you find out that C is the resultant of A and B. So since C is the resultant of A and B, I can rewrite this as, okay, so as I have this, to write the resultant of this, so the resultant is going to be this way, in the opposite direction. So which means A plus B is equals to minus C. How do I come up with this? Now, I said for forces to be in equilibrium, the sum of their forces or the resultant of the forces must be equal to zero, which means A plus B plus C will be equal to zero. Now I have A plus B plus C equals to zero. So I can also say A plus B is equals to minus C. So now this C is called the equilibrant of these two forces. Now what's an equilibrant? Equilibrant is simply a force which is equal but opposite in direction as the resultant force. So the resultant of these two forces, A and B, and then the opposite of it is equal in value, but it's opposite. That's why it's having this negative sign. You can see this negative sign here. So an equilibrant is a force that is equal but opposite in direction as that of the resultant force. So now, for example, I'm going to redraw this. This is A and this is B. And C is acting this way. So now, let me say this is going to be my resultant, and then this is C. So which means R is acting this way. The value of R and C, they are the same. Just that C is acting in the opposite direction of R, where R is my resultant. So which means C is the equilibrant of A and B. So that's how we calculate resultants of concurrent forces. So now let me say, probably I want to rewrite this as this. I have A, or let me use force 1 and then force 2. The equilibrant of these two forces, the resultant of these two forces will be here, which is going to be R. So now, for me to for me to write the equilibrant of these two forces, the equilibrant of these two forces will be somewhere here. On the same value, it will have the same value as the resultant, but then it will be in different direction, just like this. So which means F3 is the equilibrant of these two forces. So now I can say F1 plus F2 plus F3 is equals to 0. Now, this F3 I'm adding to this is making these two forces, that's 1, 2, 3, these three forces to be in equilibrium. These two forces normally are not in equilibrium. Now, adding the equilibrant to it is what is making these three forces to be in equilibrium. So I can also say F1 plus F2 is equals to minus F3, bringing this to this side. So this minus F3 is the equilibrant of these two forces. I can also say F1 plus F3 is equals to minus F2. So which means F1 plus F3 is equals to minus F2, which means this guy is the equilibrant of these two forces. F3 is the equilibrant of F1 and F2. Why F1 is the equilibrant of F2 and F3? Why? Because these three forces are in equilibrium. So that's how you calculate equilibrium of forces that are concurrent. That is, they are passing through the same point. So which means I can say this is the equilibrant of these two forces. F2 is the equilibrant of F1 and F3. F3 is the equilibrant of F1 and F2. And then F1 is the equilibrant of F2 and F3. Are you guys following me? So you can say F1 plus F2 is equals to minus F3. So you can also say F1 plus F2 is equals to my resultant force. So therefore, my resultant force is the negative value of my F3. So which means F3 is the equilibrant, meaning the opposite value, but the same value as the equilibrant. It's the same in value, but opposite in direction as the resultant. That's the equilibrant. So that's calculating equilibrium forces of of forces that are concurrent, that is, they are passing through the same point. So now, for for forces that are not concurrent, how do we calculate their resultant force? Okay, or let me just give a rough example of something like this. Let me just draw a rough example. I have this F1, F2. Or probably I'll just be doing it when we are working with examples. So now, if I move to the example section, before we move to working examples, now there's also a way you can calculate equilibrium of forces by resolving each force to the horizontal and vertical components. When I said horizontal and vertical components, what do I mean? Let me write this way. When I said horizontal and vertical component, what do I mean? You know, horizontal component, you know, that's the x-axis, and then the vertical component is the y-axis. So what I want to do is I want to resolve these three guys into horizontal component and then vertical component. So first now is to draw my line. My x-y plane. So now this is it. This is my x and this is my y. So probably this will be theta one, there will be theta two, and then there will be theta three. That's the angle at which they are inclined to the horizontals. So the angles at the angle at which these forces are inclined to the horizontal. So now I have my y component and my x component. So now I want to resolve these three forces to the horizontal component. So now it will become the sum of the resultant of all these to the horizontal component and the sum of all of these to the horizontal component. So now resolving this to the horizontal components, that's fx. I'll have taking f1. I want to start with f1 first. So f1 and theta 2. Okay, let me just, let me make this f1. It should be f2. Because they're having 2 and 2. So they're having the same sub. So let me just write it like this. So starting with f1. So f1 cos theta. Why is it? Should it be f1 cos theta? Now, there's a way you write this. Now, you remember this is positive x-axis. This is positive y-axis, negative y-axis, and then negative x-axis. So now, when you're working with the horizontal component, and then the part of the horizontal component is falling towards the side, it's going to be negative. You're going to have a negative value. When it's coming towards the side, you're going to have the positive. As when the direction is towards the positive value of the x component, the positive side of the x component, you're going to have positive. When it's towards the negative side of the y component, it's going to be negative. When it's towards the positive side of the y component, you're going to have it as positive. So what are we going to do here? So this is going to become, this is towards the negative side of the x component. So this is going to become minus f1 cos theta 1 because it's towards the negative side. Now moving to f2, this is towards the positive side. So this will be plus f2 cos theta 2. Then now this is coming to theta 3. Coming to theta 3, this is minus because it's towards the negative side. So this will be minus f3 cos theta 3. So now this is the sum of everything, sum of all these all these vectors, I'm sorry, all these forces to the horizontal component. Now summing it or resolving all of this to the vertical component, which is going to be Fy. Now for Fy, I said this is positive, y this is negative. So for F1, F1 is towards the positive y axis or y component. I see F1 sine theta 1. So F2 is also towards the positive side. The direction is also towards the positive side of the y axis. So this will be plus F2 sine theta 2. While F3 is towards the negative side. So this will be minus F3 sine theta 3. So this way you can also resolve it to the positive and vertical axis, and then you find the resultant of these two. So finding the resultant of these two, you have the equilibrium of these three vectors. So this is a way of finding equilibrium of concurrent vectors. So now moving to parallel vectors, equilibrium of parallel vectors. What are parallel vectors? Parallel forces or vectors. Okay, force is a type of vector. So I'm mistaking it for myself, but now we're just talking about forces. We're not talking about vectors generally. So we are talking about only forces. So when I'm saying forces, what are parallel forces? Parallel forces are simply forces that don't meet, just like you define parallel lines. Parallel lines are lines that don't meet. So now, what's the example? I already showed you example of a concurrent force. So parallel force are also sometimes called non-concurrent force. So now, what's a parallel force? Let me say this is a line, and this is force F1, and this is force F2. So if this is force F1 and force F2, these two lines, as you can see, they are parallel to each other. and they can never meet. So this will keep going down and this will keep going down. They can never meet. So these are called parallel forces, right? So to find the equilibrium of parallel forces, firstly, for parallel forces to be in equilibrium, the sum of the forces when resolved in every direction must be equals to 0. So now, which means, okay, let me say I have F1 here and I have F2. This is, let me say this is a pivot, and then this is, let me say F3. Let me say something like this. I have this as F1, F2, and F3. As you can see, these three forces, F1, F2, F3, they are all parallel forces. Now, for these three forces to be in equilibrium, the sum of these forces, right, the resultant force of all these forces must be in equilibrium, meaning F1 plus F2. Now, this will be plus F minus F3. Why? Because it is acting in the opposite direction as these two forces. This is acting in the opposite direction as these two forces. This is acting downwards. Why this is acting upwards? So this will be minus equal to 0. F1 plus F2 minus F3 is equal to 0. So now, for non-parallel forces to be in equilibrium, they have to the resultant forces when resolved in every direction, that's in this direction, in this direction, in this direction, that's what I did here, must be equal to 0. So now, if F1 plus F2 minus F3 is equal to 0, it means these three forces are in equilibrium. So now, another way of explaining this is, if the moment of this force around this area, when taken in the clockwise direction and when taken in the anti-clockwise direction, they are equal, it means these two forces are in equilibrium. Now, what's moment of a force? Moment of a force is simply the product of a force and the perpendicular distance through that force. The moment of the force and the perpendicular distance from that force. So let me say this is a force. So now the moment of this force, F3, is simply this force times the perpendicular times the perpendicular distance from that force. This is also a moment of a force from this point. F2 times this. So let me say this is from here to here is A, and from here to here is B. So this is moment of a force. So I said moment of a force is the product of that force times the perpendicular distance through it is act. So now F1 is acting from this point to this place, while F2 is acting from here to here. So now which means for the moment of a force, for it to be equal, or for forces that are parallel to be in equilibrium, it means the moment of a force when taken in the clockwise direction, that's this way, and taken in the anti-clockwise direction, they should be equal. So what this means here is F1 times A should be equals to F2 times B. So now here is where we are stopping in equilibrium of forces. So now in the next class, we are going to move to the calculations and working examples. So thank you for having me. Have a nice day.